Right, within this lesson, what we are going to do is look at the oxidation of the alcohols just from the bare basics of it. So, starting off with considering how we apply the idea of oxidation states and redox to organic molecules, and then looking at how we apply these basic principles to the case of the oxidation of the alcohols using acidified potassium dichromate. We will not in this video be looking at the specific experimental technique for carrying out these oxidations. This will be covered in more depth in its own video later on, most likely. Right, so first of all, oxidation states in organic compounds. So if we've um, got an organic molecule, just like any other compound, we can consider the oxidation states of each element involved, and these are the theoretical charges that each element would hold per atom should every single covalent bond within the molecule be broken and electrons be transferred as per the rules of electronegativity. Now, you've been introduced to the rules for determining oxidation numbers previously, so we can apply that within this case straight away. Hydrogen within the molecule of ethanol here, as our example, is the least electronegative, and so in each of its bonds, we're going to consider it losing its single electron to whatever else it's bonded to, and therefore hydrogen in every case is going to have a +1 oxidation state. Oxygen is the most electronegative element within this molecule, and so we will consider it gaining 2 electrons, completing its outer shell, so gaining 1 electron from the carbon-oxygen bond and 1 electron from the hydrogen-oxygen bond, so that gives oxygen an overall oxidation state of -2. Now, carbon in the middle is a little bit more complicated, so we have to apply a general principle here that the total of all of the oxidation numbers within the molecule has to be equal to the charge on the species we're talking about. Now, because we're talking about a molecule in this case, the total charge is 0, and so the total of all of the oxidation numbers is 0. Now, we know oxygen and hydrogen's individual oxidation states. For hydrogen, we've got 6 of these. So in total, the total oxidation of the oxidation numbers for all of the hydrogens is +6. We've only got 1 oxygen, so that's -2 still. And if we add those together, we get a +4 total oxidation number here. Now that means that the carbon in total must have a -4 oxidation number, but there are 2 carbons, so that's shared out between them, so that would give us each carbon being -2 in its oxidation state. Okay, so that's following the basic rules here. However, if you actually have a look at the ethanol molecule, you might begin to see a little bit of a problem with this, because clearly the carbons within this molecule are not equivalent in terms of what they're bonded to. We've got 1 carbon which is bonded to 3 hydrogens and 1 carbon, so none of these are going to be particularly pulling electrons away from that carbon, whereas this carbon here is bonded to 2 hydrogens, yes, but it's also bonded to an oxygen, which is definitely going to be quite effective in pulling electron density away from it. We would expect, if we broke all of the bonds in this molecule and electrons were transferred to the most electronegative atom within each bond, we would expect that this carbon ought to not have ought to have a more negative charge than this carbon should, because this carbon being bonded to an oxygen is going to be losing an electron to that oxygen that this carbon is not going to lose. So we need a slightly different method for determining the oxidation states for each individual carbon in the molecule. And the way that we can do this is essentially by dividing the molecule into sections, each containing 1 carbon. and saying that each section has the total oxidation state equal to the charge of that section. So in this case, we have to have a total of 0 for this section and a total of 0 on this section. Now, if each of these hydrogens within this section is +1, that means this carbon is in a not a +3, but a -3 oxidation state. Now, in this section here, we've got +1 hydrogen, +1 hydrogen, +1 hydrogen, so 3 +1s, but we've also got a -2. So that comes together to give us overall a +1. So +3 -2 +1. So this carbon here is going to be -1 overall. Okay, so we can see now from this method that we get the difference between the two, the difference in oxidation state between these two carbons, which is what we would expect here. So this is clearly the better way of dealing with this. Let's have a look at another example then. So let's have this molecule here. Okay, so in this molecule, we would need to again divide it up into sections, each containing only one carbon. We note here that we've got a little bit of a complication because this oxygen is actually shared by both. So we're going to consider this oxygen's to be acting as -1 on this side and -1 on this side rather than -2 in either of them. The oxygen's effect is shared out over those two sections. Okay, so what do we have here? So we've got +1 hydrogen, +1 hydrogen, +1 hydrogen. So carbon here is going to be -3, very similar to as before. In this case, we have a -2 oxygen and a -1 oxygen, so that's -3 in total. So the carbon is going to be equal to +3. And lastly, we've got +1, +1, and +1, but then we've got -1 from the oxygen. This single bond here to this oxygen, the carbon is losing 1 electron to the oxygen there. So that means total oxidation state here is +2 overall. So the carbon is -2 in its oxidation state. That means that the average of the oxidation state for carbon, well, we've got +3 here, we've got -3 here, so that completely cancels out. And then we have -2, which is then shared between each of the carbons. So actually, the carbon has an average oxidation state of -2/3 for this molecule. And you can see that this works in the previous example as well. So the individual oxidation states of these two carbons are -3 and -1, and that, of course, averages out to -2. So if you use the first method of determining the oxidation number within of carbon within this molecule, you would have gone straight to this particular figure here of -2/3. Okay, so let's move along. Now, That is one way of dealing with oxidation and reduction within organic molecules. And of course, it is very, very useful to be able to do that because it will allow you to write out the actual redox half equations for any reactions that you're going about. That you're going about. However, it is a little bit intensive in terms of determining things. So we tend to use within organic chemistry a little bit of a more rule of thumb way of identifying levels of oxidation um, for carbons. And here we employ something that we call functional group levels. Now, functional group levels basically is determined by the number of bonds to a heteroatom. And this simply means an atom not H or C, and will therefore usually be more electronegative. So if we started off with, say, an alkane, here we have no heteroatoms, and so we would say that the carbons within the alkane are on a functional group level of 0. Okay, which corresponds to the lowest oxidation level. If we then go up to an alcohol, such as ethanol, the functional group in this case, so we're looking, of course, at this bit here, the carbon bonded to the functional group has a single bond to a heteroatom, that being oxygen in this case, so that gives us a functional group level of 1. This can be applied to other organic molecules as well. So, for example, halogenoalkanes would also fall on a functional group level of 1, as would amines. Okay, so just considering the functional groups in each of these cases. Okay, so then it becomes relatively clear where we're going with this. So the next level up, we could have, for example, a dihalogenoalkane like this, where the carbon has 2 bonds, 2 heteroatoms, and so this gives us a functional group level of 2. Similarly, this could be achieved by having a double bond to one heteroatom. So this would also fit within a functional group level of 2. You effectively have 2 bonds to a heteroatom through a double bond to that heteroatom. Okay, and finally, this would also include species like this, which you will already be familiar with. if we consider the functional group within this molecule here, we've got 3 bonds to heteroatoms, so we have a functional group level of 3. Okay. So this could also look, for example, like this. Or you could also have something that looks like this, which would all sit up at a functional group level of 3. Or even you could have something that looks like this, where X is a halogen, for example. That would also be at a functional group level of 3. And you can extrapolate from here to functional group level of 4 as well. So that could be where you've got, for example, tetrachloromethane, carbon bonded to 4 chlorines. That would be a functional group level of 4. Or you could have carbon dioxide, also functional group level of 4. The carbon has 2 double bonds to oxygen, so it has in total 4 bonds to heteroatoms. Now, this is really nice way of looking at oxidation and reduction in organic molecules, because you can easily identify the functional group level, and essentially this gives you a very quick way of assessing whether you've got oxidation or reduction. So anything where the functional group level increases is an oxidation reaction, because if you increase the number of bonds to more electronegative atoms within the molecule, if the carbon is bonding to more atoms that can pull electrons away from it, then its oxidation state is going to increase. Whereas conversely, if the functional group level decreases, then we've got reduction. Okay, so that gives you a nice and quick way of assessing whether you've got oxidation or reduction. Right, so from the functional group level way of understanding oxidation and reduction, you can get a simple idea about how we might go about oxidizing organic compounds. Essentially, the process will usually involve the removal of hydrogen or carbon atoms and the replacement of those hydrogen or carbon atoms with heteroatoms, therefore increasing the functional group level of the molecule. And as such, you might wonder about how alcohols might be oxidized. So in the case where we talk about the oxidation of alcohols, we are actually talking about the introduction of additional bonds to oxygen atoms. And so if we started off with an alcohol with this structure, you might expect the outcome of oxidation to produce something that looks like this, where one of the hydrogens is replaced with another OH group. So that would increase your functional group level by 1, therefore being an oxidation. You've taken off a hydrogen and you've replaced it with an OH group. This particular molecule that I've drawn out here turns out not to be very stable. It's known as a geminal diol. Geminal basically refers to 2 functional groups being attached to the same carbon. So you can refer to these hydroxyl groups, these OH groups, as being geminal to each other. Geminal diols are in fact not stable because there's kind of like a tug of war of these oxygens and the electrons within the bonding system here. And eventually, if there is a slight perturbation of the system, if there's a bit of a disruption, so let's say that this molecule collides with another molecule, electrons end up moving moving in one direction or the other, towards one oxygen and away from the other. So what we end up with is a chain of curly arrows where electrons move towards one oxygen, and then it uses its lone pair to pick up the hydrogen from the other hydroxyl group, and then that hydrogen breaks off from the oxygen in that hydroxyl group. And what ends up occurring is a rearrangement reaction, which gives us this molecule, as well as a water molecule which has broken off. Now, what you see is that your geminal diol has been converted into this C double bond O group. This is at the same functional group level as the geminal diol, which is level 2. So no oxidation or reduction has occurred here. It's still on the same oxidation level, if you like. But we've carried out this rearrangement that gives us this functional group C double bond O, which is referred to as a carbonyl. Now, carbonyls come within two flavors. This here would be an aldehyde, but you can also have ketones where you've got two R groups. And these are the functional group level above the alcohols. And this just generally turns out to be the case, is if you've got two hydroxyl groups bonded to the same carbon, they will tend to break down to give you a carbonyl functional group instead, either an aldehyde or a ketone, depending on what the rest of the carbon chain is doing. Okay, so for a ketone, you'd have to have two carbons bonded to the carbon with the functional groups on it. So that's just something to note here. So geminal diols are unstable, so we don't really see them. They always break down to give you a carbonyl and water. Right, we'll come back to why that might be useful to think about in a little while. Let's move along. Okay. Now, the type of oxidation that we're going to look at in specific in this section is the oxidation of alcohols by acidified dichromate 6 ions. Now, dichromate 6 has the formula Cr2O7 to minus. I do not do silly typos. Okay. And it has chromium within the +6 oxidation state here. And it's the chromium that actually is carrying out the oxidizing in this particular reaction, where the chromium is accepting electrons and being reduced to a lower oxidation state. So it's going to take electrons away from our alcohol, and it's going to be reduced to a lower oxidation state. Now, the lower oxidation state that it's reduced to is 3+ in the form of chromium 3 ions. So let's try writing out a half equation for this. So you've got Cr2O7 2 minus, and that's going to be converted into Cr3 plus. First thing to do, we got to identify the oxidation states of our chromium. So we've got +6 here and we've got +3 here. So we know that we have got a -3 oxidation state change for each chromium, but we've got 2 chromiums. So I'm just going to balance that up there. So that's -6 overall. So on this side, in order to get that -6 oxidation state change, I have to have +6E- to account for that. So that's the redox aspect of this half equation balanced up. Then we need to just sort out our unbalanced oxygen atoms. So we've got 7 of these. So we're going to have +7H2O being formed. And therefore, on the left-hand side, I'm going to have 14H plus provided. Now, having written out this this half equation, you can see why we specify that for this oxidation, the dichromate 6 has to be acidified. Okay, this is done by providing H plus from H2SO4. So you have to have a mixture for your reaction. You have to have your some provision of your dichromate ions, and you have to have a provision of H plus from H2SO4 as well. The H plus is required for this reduction to occur so that the dichromate can oxidize your alcohol. Now, one thing that's interesting to note within this reaction is that we're dealing with transition metal ions here, which have colours. The dichromate itself is orange, and the chromium 3 plus, which is produced, usually produces a greenish colour. Okay, so when this reaction is being carried out, when you've got your acidified dichromate 6 mixed in with your alcohol and it's oxidizing the alcohol, a sign of the reaction is the transition of the orange dichromate 6 into green chromium 3 ions. So that's a nice change that you can observe. Now, dichromate 6 is only the effect that it has on the alcohol is that it incorporates additional bonds to oxygen as it oxidizes the alcohol, and it breaks bonds to hydrogen in the molecule. It is not a powerful enough oxidizing agent to break the carbon-carbon bonds. So that gives us some limitation on how much oxidation that this dichromate can produce. It's not going to completely break down your alcohol into carbon dioxide. It's just not a powerful enough oxidizing agent. You're only limited to breaking carbon-hydrogen bonds with this particular oxidizing agent. And also, you're not going to be attacking any of the alcohol groups within your alcohol molecule as well. This only affects the carbon with the functional group. So the one that the hydroxyl is bonded to. Right, so let's have a look at oxidation of different alcohols then. Now, we are aware, I hope by this point, that there are 3 different types of alcohol that you may come across, which I am going to represent like so. We've got our primary alcohol, our secondary alcohol, and our tertiary alcohol, which you will note have different numbers of hydrogens bonded to the carbon bonded to the functional group. So here the carbon that's bonded to the hydroxyl is directly bonded to 2 hydrogens. So in the oxidation reaction, these carbon-hydrogen bonds can be broken. For the secondary alcohol, it only has a bond to 1 hydrogen. And for the tertiary alcohol, there are no direct bonds between this carbon and hydrogens. Right, now, when we carry out an oxidation, we take off one of the hydrogens, we break a carbon-hydrogen bond, and we introduce a new bond to oxygen. Now, usually that would involve introducing a new OH group, but if you note here, if I were to replace one of these hydrogens with an OH group, that would produce a geminal diol, and we know that geminal diols are not stable, so what will happen instead is I produce a carbonyl group where I used to have the hydroxyl group. Okay, so I end up with a molecule that looks like this. A similar thing will happen when we attempt to oxidize a secondary alcohol. So in this case, we take off this hydrogen, and the hydroxyl functional group is replaced by that C double bond O carbonyl functional group. Now, if we go to the tertiary alcohol, we will see that we don't actually have any hydrogens to break off. If we wanted to oxidize this further, we actually would have to break a carbon-carbon bond. And acidified dichromate is just not a powerful oxidizing agent enough. You would need a more powerful oxidizing agent. So tertiary tertiary alcohols cannot be oxidized by acidified dichromate. There'll just be no reaction. If you try and mix your nice orange acidified dichromate solution with your alcohol, it'll just stay orange because it just can't oxidize a tertiary alcohol. Whereas with primary and secondary alcohols, you would see that acidified dichromate change from orange to green as it oxidizes the alcohol that is present. Now, if we have a look at the products of oxidation for primary and secondary alcohols, we can see here we have an aldehyde, as we have a carbonyl group next to a carbon-hydrogen bond, and from the secondary alcohol we get a ketone, where the carbon in the carbonyl group has 2 alkyl groups attached to it. It's got 2 carbon-carbon bonds. Okay, now we're not actually quite done yet, because if we have a look here at the aldehyde, we've still got a hydrogen here. So that can be, again, broken off by our oxidizing agent and replaced with a new bond to an oxygen. So what do we end up with? And we can see that we've made a carboxylic acid. So aldehydes can be further oxidized into carboxylic acids. How about ketones? Well, at this point we have no hydrogens left bonded to that carbon, and therefore no further oxidation is actually possible. Again, like the tertiary alcohol, we would need a more powerful oxidizing agent. Acidified dichromate just can't take this any further, as it can only oxidize carbons in the functional group that have hydrogen bonds to hydrogen as well, and there are just no more bonds to hydrogen for this particular carbon. Okay, so primary alcohols can be oxidized twice, to aldehydes and then to carboxylic acids. Secondary alcohols can be oxidized once to ketones, but no further. And tertiary alcohols cannot be oxidized at all by acidified dichromate.